The title of this presentation is Integrability of a Hamiltonian Flow for the Inhomogeneous Six-Vertex Model. To begin with the presentation overview, we'll be introducing the six-vertex model, the R matrix, and a Hamiltonian flow for the six-vertex model. And we'll be drawing upon similarities from computing the action angle variables from previous methods that were described for the nonlinear Schrodinger's and the Kamasa-Holm PDEs. And we'll be trying to motivate and describe how, even though there can be many differences in how a partial differential equation is defined and how the six-vertex model and inhomogeneities are introduced in the six-vertex model, at the core, there are actually many similarities for demonstrating integrability and solvability of both of these types of systems relating to the Poisson bracket and action angle variables. And we'll be discussing aspects of a conjecture for integrability of the Hamiltonian flow from the inhomogeneous six-vertex model, which was raised in a 2020 paper, which I think was published in 2022, that was discussed by Keating, Reshettikin, and Sridhar. And in this paper, at the end of the paper, the authors conjecture that the Hamiltonian flow that they introduced for the six-vertex model would be integrable, but they just only mention in a sentence that we should look to some reference, which is a Springer text, which I'll be referring to and drawing and incorporating in our discussion about how one can deduce integrability of this Hamiltonian flow for the inhomogeneous six-vertex model from the action angle variables and how this relates to the method that was carried out for the nonlinear Schrodinger's equation. And in doing this, we're going to provide an overview of computations with the action angle variable and the Poisson bracket. So we're going to be making use of many standard properties of the Poisson bracket in determining how these relationships for the Poisson bracket would be related to the entries of the monodromy matrix and how the entries of the monodromy matrix relate to the construction of the transfer matrix, which is ultimately rooted in the R matrix for the six-vertex model, which we're going to all break down. So the first reference that we're going to be looking at is a reference that's not mentioned in the paper by Keating, Reshettikin, and Sridhar, but it nevertheless adds in a lot of very informative content, comments, and structure about the type of argument that we're going to be pursuing using the Poisson bracket and how these computations in the Poisson bracket relate to different partial differential equations and how one can demonstrate that integrability or solvability holds from certain structures of a partial differential equation. And this reference from a Springer link is given by Poisson structure and action angle variables for the Kamasa-Holm equation by Konstantin and Ivanov from 2006. And it's demonstrating to us how one can make use of the Poisson bracket to demonstrate that some type of integrability or Poisson structure holds for the Kamasa-Holm partial differential equation in terms of the action angle variables and expressing these action angle variables in terms of the scattering data. So even though, as we had just mentioned in the introduction, one may think that there may not be so many similarities in applying this structure or carrying out certain computations with the Poisson bracket in terms of a partial differential equation or the six-vertex model, these arguments are actually very much follow a similar type of structure that we can also implement for demonstrating that integrability holds for a Hamiltonian of the inhomogeneous six-vertex model, which is a completely different type of system rather than the partial differential equation that these authors look at in their 2006 reference for the Kamasa-Holm PD. And just to give a little bit of the background for your culture, as some people say, the Kamasa-Holm PD is a third-order partial differential equation that's given by this relation. And originally, I was immersed, or I was exposed to the Kamasa-Holm partial differential equation when I was looking to perform some numerical simulations for roughly determining how the solutions would look at from a quantum algorithm that I was studying and coding up in a completely different project. But even though I looked at this partial differential equation first in a completely different area, it actually has a lot of relation to the six-vertex model, and how one can look at introducing inhomogeneities for the six-vertex model and deducing that the six-vertex model Hamiltonian flow is integrable. And in particular, the first connection or link comes from the fact that one can look at making a Hamiltonian formulation for the Kamasa-Holm PDE, in which if one introduces an M term, which is given by the difference of the solution of the Kamasa-Holm equation with the second derivative of the solution, then one can introduce two Hamiltonians, which can help us parameterize, will introduce a parameterization of sorts for the Kamasa-Holm partial differential equation, which then allows us to perform different types of computations with the Poisson bracket for deducing that some type of Poisson structure exists for the Kamasa-Holm PDE. So this is just demonstrating that from the statement of the Kamasa-Holm partial differential equation and introducing an M term, which is given, as we had just mentioned, the difference of the solution U minus the second derivative of the solution, we can look at how to formulate and repackage the Kamasa-Holm PDE in terms of two Hamiltonians. And this is very much part of the strategy that's introduced for the six-vertex model, in which although we won't explicitly introduce the Hamiltonian flow, there can be a way to introduce a Hamiltonian flow for the inhomogeneous six-vertex model, from which one can make use of action angle variables in the Poisson bracket for deducing that integrability holds relating to the monodromy transfer matrices, which we will explicitly write out. And as we've been mentioning along the lines of our previous comments, similar methods by which one can introduce notions of solvability and action angle variables for the Kamasa-Holm PDE relate to computations with a Poisson bracket for the six-vertex model. So this is just showing that even though these systems can be phrased and packaged very differently, because the Kamasa-Holm partial differential equation is a PDE in which one's looking at the time evolution of the solution and relating it to several nonlinearities, and the six-vertex model is introduced from a probability measure, they can ultimately be related to one another from the arguments that we're going to show for demonstrating that integrability holds from the Poisson bracket. And the reference that we're going to be using for the inhomogeneous six-vertex model is the following. It's another Springer reference by Keating, Reshettikian, and Sridhar, in which is titled Integrability of Limit Shapes of the Inhomogeneous Six-Vertex Model. So this is just demonstrating how they make use of these different type of components that we've been demonstrating, namely the Hamiltonian flow, the six-vertex model, and how one can introduce inhomogeneities in the six-vertex model for being able to deduce that the limit shape of the model is integrable. And even though that they didn't deduce that the Hamiltonian flow of the model is integrable in their paper, they say at the very end that it would be a very interesting prospect for future research to determine what type of integrability and the properties that integrability would hold for the Hamiltonian flow, and that they conjecture that this Hamiltonian flow is integrable. So I'm going to be demonstrating how we can make use of their previous work on the integrability of the limit shapes to demonstrate that integrability of the Hamiltonian flow also holds. And now we can actually begin to introduce the model, in which the six-vertex model will first provide like a pictorial, more informal definition of it, and then we'll go into like some more specific characteristics and structure of the model. But it was introduced originally by Linus Pauling, who's a chemist, and he was interested at looking at like various configurations of hydrogen and oxygen atoms together in the plane. And these configurations of the six-vertex model satisfy the ICE rule, which is given by the constraint that about every vertex in the square lattice, there are two arrows pointing in and two arrows pointing up. And this is given by the six possible configurations as given on the top line, in the top image of this slide. And as one can see from this paper that's taken from another paper on the height function of the six-vertex model, which was produced by Dumano, Copan, Carrillo, Manolescu, and Ulamara, they label each one of the quadrants as 0, -1, or -2, because this depicts the value of the height function in a quadrant of the square lattice, and how the value of the height function would either go up or down by 1, increase or decrease by 1, depending upon the orientation of the arrow that it crosses. But below that, there's also another depiction of the six possible weights of the six-vertex model, which is provided in the reference for the inhomogeneous six-vertex model due to Keating, Reshettikian, and Sridhar that we introduced from the Springer reference, which also depicts another possible way to depict the six possible configurations of the six-vertex model through line configurations. So this is a little bit different in that we're not depicting in the line, in this depiction in the second figure on the slide, we're not depicting the orientation of the arrows, but instead we're depicting whether there's a solid line, which indicates that the arrows are all pointing this way or all pointing up, or in the other type of configuration, none of the arrows of the or none of the edges that are incident to the single vertex of the square lattice are colored because they're oriented in the opposite way, namely one edge is going this way and the other one is going down instead of up. And one can look at different types of combinations of these configurations for the six-vertex model for demonstrating that a line configuration can be depicted this way instead of an arrow configuration. So it's just very much another way in which some any one of the possible six configurations of the six-vertex model are shown. But furthermore, we can introduce the model over the torus, in which over the torus we have a vertex set and some edge set. And the six-vertex model can be defined with a probability measure, which is given by this, which is the weight of a configuration normalized by the partition function, so that W of omega divided by the partition function is a probability measure. And the weight of the six-vertex model for some configuration is given by A1 to the N1, A2 to the N2, B1 to the N3, B2 to the N4, C1 to the N5, and C1 to the N6, or C2 to the N6. So this is demonstrating that each one of these factors, which is included as one of the six factors which are multiplied together to form the weight of the six-vertex model, is given by a strictly positive parameter A1, A2, B1, and B2, and C1 and C2, and N1, N6, N3, N4, N5, and N6 are each respectively the number of vertices of each type in a six-vertex configuration that we take over some finite volume of the square lattice. But besides these basic definitions for the six-vertex model, the inhomogeneities can be introduced with the following construction with the R matrix. But before we introduce the R matrix, which is inherently parameterizing the weights of the six-vertex model, we have to look at a disorder parameter, which is given by A1 to the A2 plus A3 to the A4 minus A5 to the A6, which is divided by 2 to the square root of the product of the four weights. And this is important because this is a parameter that's used to distinguish between several different characteristics of the phase diagram of the six-vertex model, in which in another presentation on the channel that I've given, Dumino, Copan, and co-authors conjecture as to what the phase diagram of the six-vertex model would be, in which the model can potentially exhibit ferroelectric or anti-ferroelectric phases, depending upon the value of this disorder parameter that we take. And a lot of the values that this disorder parameter are taken relative to is a -1. So in this case, when we're demonstrating that the integrability of the Hamiltonian flow for the inhomogeneous six-vertex model holds, it's going to be with this parameter taken strictly to be less than -1. And in the presence of two external fields, we can introduce the following parameterization for the six-vertex weights. So we can take the six weights that we use to define a configuration for the six-vertex model, and we can parameterize them in terms of exponentials of these two external fields H and V, and we can take H plus V minus H minus V, H minus V minus H plus V. And for the last two weights, we can also take another strictly positive parameter lambda and either take lambda or the reciprocal of lambda. And we can form the R matrix by taking a 4x4 matrix, and the matrix is mostly sparse because along the diagonal we have these terms, which is a to the exponential a plus b, b to the exponential h minus v, b to the exponential minus h plus v, and a to the exponential minus h minus v. But along the two terms that are closest, along the anti-diagonal that are closest to the diagonal, we have c, which is given by the C1 and C2 weights for the six-vertex model, and the rest of the entries of the R matrix we take to be 0. And the R matrix is important because it satisfies the Yang-Baxter equation. There are many different types of interpretations for the Yang-Baxter equation, but for our purposes, a great way to look at things and to be able to discuss how the Yang-Baxter equation fits into the definition of the model is that it satisfies an intertwining relation, which is given by for the fact that the R1 of 3 term of U plus V is the same on both the left-hand side and the right-hand side of the equation, but we can interchange the R1 of 2 term with the R2 of 3 term, which is given by on the left-hand side of the equation with R2 of 3 and R1 of 2 on the right-hand side of the equation. So this is one of the equations that's going to come into play. But another equation besides the Yang-Baxter equation is that there's also a relation for solutions that are determined by the beta equation, which is related to the beta ansatz. And the beta equation is a system of equation which is given by the following statement. We have a product of a ratio of hyperbolic sign where the argument in the hyperbolic sign that's appearing in the numerator of the expression is given by 8/2 plus I alpha j minus vk. And then in the numerator, the argument for the hyperbolic sign is almost the same, except it's a minus alpha I alpha aj or I alpha j plus vk. And then we also have an exponential, which is dependent on one of the external fields that we introduced in the parameterization of the six-vertex weights, which we introduced a couple slides ago. But there's also another product of the ratio of hyperbolic sign functions in which we're only restricting ourselves to take m not equal to j. But there are in the product, we're taking all of the other terms from m is equal to 1 to n. And the expression for the eigenvalues of the beta equation take the following form. This is directly provided to us from the reference for the inhomogeneous six-vertex model, in which the authors can introduce a parameterization and write down explicitly what the eigenvalues for the solutions to the beta equation are, depending upon the ratio of these two hyperbolic sign functions, as well as the h, which is one of the external fields for the six-vertex model that, again, we introduced for the parameterization of the weights. And the last term is given by another term that's dependent upon one of the external fields, as well as the product of the hyperbolic sign and a product of a ratio of two hyperbolic sign functions, where we introduce some slight difference in the parameter that we use to evaluate the hyperbolic sign of in the numerator of the expression in comparison to the denominator of the expression. And now we can proceed to define some other quantities so that we can make more explicitly and clear those similarities between the Kamasa-Holm partial differential equation as well as the nonlinear Schrodinger's equation in our quest or our pursuit to determine whether integrability for the Hamiltonian flow of the inhomogeneous six-vertex model holds. And the Hamiltonian flow, it can be defined in a similar type of way that is also provided from the paper reference that we've been discussing in the Springer reference due to Keating, Reshettikin, and Sridhar. And we're going to begin by looking at the quantum monodromy matrix, which is given by the following function, which is dependent upon some spectral parameters u and some collection of local variables v sub k for each site k, as well as the two external fields that we use to parameterize the weights of the six-vertex model h and v. And this is given by the fact that this 2x2 matrix admits the form A of u, B of u, C of u, and D of u. And there's a very similar form, which we'll also allude to, which is used for determining that integrability holds for the nonlinear Schrodinger's equation and even for the Kamasa-Holm partial differential equation. And then once we can make use of and think about these connections more clearly, it very much becomes a game of being able to use the Poisson bracket on the action angle variables and determining how the specific entries of the quantum monodromy matrix relate to how we can compute these action angle variables and what would the expressions be from the Poisson brackets that we're going to introduce later on in the presentation. And so we can transition from the quantum monodromy matrix to the transfer matrix, in which the transfer matrix is defined as the trace with respect to A, which is some strictly positive parameter of the monodromy matrix multiplied by n diagonal matrices. And I'm not going to exactly define what the diagonal matrices are, but they're provided within like the first 5 or 10 pages of my paper, in which I reference the explicit form of the diagonal matrices that are used for the construction of the inhomogeneous six-vertex model in the paper by Keating, Reshettikin, and Sridhar, in which they look at the product of these diagonal matrices and they multiply by the trace of the monodromy matrix to obtain the transfer matrix, which is also dependent upon the spectral parameter u, the collection of local variables v sub k, and the two external fields. So now we're going to be making use of and introducing another reference, which is brought to our attention by the Keating, Reshettikin, and Sridhar reference, in which they draw our attention to a Springer reference for computing the action angle variables for the nonlinear Schrodinger's equation. So this is the reference, and it's a pretty long reference, almost like 605 pages. So it's very important to break down and demonstrate which chapters and portions of this 605-page book are important for computing the action angle variables, and specifically where the computations of the Poisson bracket come into play and how we can carry those over for the Hamiltonian formulation and the Hamiltonian flow, the inhomogeneous six-vertex model. And so they look at the integrability of the Hamiltonian flow for the nonlinear Schrödinger's equation. So it's given by the imaginary time evolution of the wave function, which is equal to minus the second derivative of the wave function plus some nonlinearity. And this chi term is a strictly positive term, which is referred to as a coupling of the nonlinearity of the absolute value squared of the wave function times the wave function. And from the Springer reference, we can compute the action angle variables from the nonlinear Schrödinger's equation by looking at the infinite volume limit of the monodromy matrix, which is the limit as Tn of lambda goes to infinity, which is T of lambda, which expressed in terms of a limit as x tends to positive infinity and a limit as y tends to negative infinity of this product of quantities, namely this T guy, which is the transfer matrix, as well as multiplied by another parameter ey of lambda and e minus x of lambda. And these two e terms are related to the fact that they can be obtained by taking a matrix exponential, which is related to a way that the nonlinear Schrödinger's equation can be expressed in terms of matrix form. And as we had just alluded to in the previous slide, the quantity E is dependent upon the solution of the nonlinear Schrödinger's equation in Pauli matrices, and specifically it's a matrix exponential where this U1 term is one of the Pauli matrices, in which is given by zeros along the diagonals and -1 along the antidiagonal. So this is a term that's involved in taking the infinite volume limit of the monodromy matrix, and this is going to relate to the Poisson bracket and taking the tensor product of the reduced monodromy matrices in the Poisson bracket, and then this will exactly imply integrability of the nonlinear Schrödinger's equation, which we can carry over to perform different types of computations for the integrability of the Hamiltonian flow for the inhomogeneous six-vertex model. So this is to say that in terms of the solution, which is the wave function C for the nonlinear Schrödinger's equation, we can define a Hamiltonian, which is dependent upon whatever position x we're in the finite volume. And the wave function, as well as the complex conjugate of the wave function and the coupling, which is given by an integral over the real line of multiplying the first derivative of the wave function and the derivative of the complex conjugate of the wave function plus the coupling times the complex conjugate of the wave function squared times the wave function squared. So this is again demonstrating a way, as we had exhibited for the Kamasa-Holm PDE, to be able to introduce a Hamiltonian formulation for a partial differential equation, which can also hold directly from the Hamiltonian formulation, which is given by Keating, Reshetikhin, and Sridhar for the inhomogeneous six-vertex model, and how these all relate to making some use of the Poisson bracket, and the Poisson structure for deducing that integrability the Hamiltonian flow holds. And to compute the action angle variables for the nonlinear Schrödinger's equation along the lines of what we've been mentioning and reiterating several times, much like those for the Kamasa-Holm, a partial differential equation mentioned at the beginning, we also need to make use of the tensor product of the Poisson bracket. So this is given by the fact that if we take two reduced monodromy matrices, T of x of lambda, Txy of lambda, and Txy of mu, the Poisson bracket of the Poisson bracket of the tensor product of these two reduced monodromy matrices, can be expressed in terms of the Poisson bracket of this R quantity with the tensor product of the reduced monodromy matrices. So we're going to be making use of very similar types of identities as these in different ways to relate the Poisson bracket of the tensor product, and how several types of relations can be deduced and degenerate from the tensor product of the Poisson bracket to just many Poisson brackets, which we can compute in terms of the action angle variables and entries of the monodromy matrix, which will allow us to determine and to deduce and to conclude that integrability holds. And the Poisson bracket can take a couple of forms, and we make use of many different types of forms in the paper. But some of the forms are that if we want to look at the Poisson bracket between two functions f and g, it can be expressed as I times an integral over minus L to L times this difference of derivatives, which in terms of the Schrodinger's equation, we take the derivative of the function f and we differentiate it with respect to the wave function, which solves the Schrodinger equation for the PD with the imaginary time evolution that we mentioned, as well as the fact for the other term in the Poisson bracket, we look at the derivative of g with respect to the complex conjugate of the wave function. And then in the other term for the Poisson bracket under this integral from minus L to L, we also look at reversing the order the variables that we differentiate f and g with respect to. So it's very much like a type of anti-commutativity term, which is relating to the Heisenberg's uncertainty principle and the fact that we can't have infinite precision at the momentum and position of the particles at the same time. But besides this expression for the Poisson bracket for between f and g, we can also look at this expression for the Poisson bracket of the tensor product between a and b, where a and b again are just any arbitrary functions. And this is given by the fact that we can similarly write the Poisson bracket as an integral times I over minus L to L, but the only difference is that we inject a tensor product between the first and second derivatives. So that's the only way in which the Poisson bracket and the tensor product of the Poisson bracket differ, just from these tensor products that occur between these derivatives that we subtract. And we can take the Poisson bracket of the reduced monodromy matrix, and this is given by the fact that we can express either the reduced monodromy matrix with a minus subscript or a plus subscript, which is just looking at the difference in whether the variable x goes to infinity or minus infinity. And in each case, we can write the tensor product of the Poisson bracket in terms of subtracting two tensor products. One of them is taking r times t to the minus x of lambda tensor product with t to the minus x of mu minus t minus to the x of lambda tensor product with the t minus x mu r minus lambda mu. And then we can obtain a similar expression for the tensor product of the Poisson bracket for the plus reduced monodromy matrices instead of the minus ones. And the L operators in the reduced monodromy matrix come into play because the L operators was introduced by another reference, which I referred to in the paper, which is a really interesting and informative reference because it talks about six-vertex model under domain wall boundary conditions and how to look at introducing an L operator and to make use of this L operator, which is dependent upon the Pauli matrices and the Pauli operators. And then this very much allows for us to make a connection with the monodromy matrix and how we can look at obtaining explicit expressions that we can make use of in terms of the Poisson bracket for carrying out several types of computations for deducing that integrability of the Hamiltonian flow holds for the inhomogeneous six-vertex model. In this case, the L operator is defined in terms of some spectral type parameter lambda alpha, as well as the collection of local variables like what we introduced earlier, b sub k, and is given by a 2x2 matrix. And the first entry along the diagonal is dependent upon some sign parameter, which is, and the argument that we take in terms of the sign is one of the Pauli operators, and the other argument is also proportional to a minus eta times a Pauli operator. And the entries on the off diagonal are given by a sign of 2 eta of different Pauli operators, namely either sigma minus or sigma k minus or sigma k plus. And we're looking at how to make a relation of this to the monodromy matrix that was introduced in the inhomogeneous six-vertex model from Keating, Reshettikian, and Sridhar. So we're going to be able to look at several relations between the entries of the monodromy matrix for the L operators can be determined by computing the following sequence of matrix products. We're just going to be looking at the relation for the first, second, and third entries, which were given in shorthand as 1 sub i, 2 sub i, 3 sub i, and 4 sub i from this product of 2x2 matrices, and relating it together, which can allow us to guide, which can allow us to compute different types of things with the Poisson structure from the entries of the monodromy matrix. So we provide a recursive definition of the entries of the nth monodromy matrix in terms of the entries of the nth minus 1 monodromy matrix, all the way down to the entries of the third monodromy matrix in the recent preprint that I made. to determine how we can break down and make use of the Poisson bracket for deducing that integrability of the inhomogeneous six-vertex model holds from the conjecture that was raised by Keating, Reshetikhin, and Sridhar. And this is just to say, as we've been mentioning, that we want to make a connection between the L operator and this nth-fold matrix product of 2x2 matrices. And we can look to make use of different type of structure of the L operators and relate that to the Poisson bracket and the action angle variables and the Hamiltonian flow and the boundary conditions in homogeneities in the six-vertex model. So we can return to the Poisson bracket, which, as we had listed earlier, we can also look at taking the tensor product of the Poisson bracket for the monodromy matrix of the six-vertex model with inhomogeneities that we introduced earlier, and it can take a very similar form to what we looked at earlier. Namely, we can look at a little r times the times the monodromy matrix, which is tensor product with the monodromy matrix at another parameter u prime, another spectral parameter u prime, as well as subtracting the monodromy matrix at u tensor product with the monodromy matrix at u prime times r to the a minus of vk minus vk prime. So this is just a way that we can write the Poisson bracket of the tensor product in terms of a different type of monodromy matrix to take the tensor product of two monodromy matrices under the Poisson bracket. And in the Poisson bracket from the previous slide, we defined the two quantities r plus and r minus as the following infinite limits. We can either take a limit as y tends to positive infinity or a limit as y tends to negative infinity of some quantity E6 vertex, where E6 vertex is like the matrix exponential that we introduced from the Springer reference for the Hamiltonian methods that allowed those authors to deduce that the integrability holds for the nonlinear Schrodinger's equation. But there's just a different way to write down what this quantity is in terms of the beta equations and how they relate to solutions of the beta equations and the eigenvalues, which are related to the transfer matrix that we introduced from the six-vertex model, which is ultimately rooted in the trace of the monodromy matrix. So this is just a way in which we can make connections between similar types of quantities for one model to the next, whether it be from a PDE to the inhomogeneous six-vertex model, but we have to look at and be careful to properly introduce the tensor product, which is given from the tensor product of the reduced monodromy matrices at the six-vertex model, and how that relates to these limits as y tends to positive and negative infinity with RA plus and RA minus. So the 16 relations follow from entries of the monodromy matrix, which is given by the fact that if we want to write out the Poisson bracket of the tensor product of these two reduced monodromy matrices, the tensor product under the Poisson bracket degenerates to 16 Poisson brackets that we can use to compute the action that we can use to compute several types of relationships with, which can allow us to deduce that integrability holds. And one can perform several computations to establish that these 16 relations in terms of the monodromy matrix of the six-vertex model can be related in terms of this recursive definition that I provided, or that I alluded to, that we obtained for the monodromy matrix in terms of the L operators under domain wall boundary conditions, and how these two relations can be used to demonstrate that certain properties, certain desirable properties of the Hamiltonian flow for the six-vertex model hold from computations of the Poisson bracket. And when performing our computations, we heavily make use of the following properties of the Poisson bracket. If we're taking the Poisson bracket of two functions f and g, it's equivalent to minus the Poisson bracket of g with f, as well as a bilinearity property, which is saying that af plus bg for the first argument of the Poisson bracket with the second argument of the Poisson bracket can be expressed in terms of af of h plus bg of h. And then another rule, which perhaps we make use of the most heavily in several of the computations with the Poisson bracket from these 16 relations that were given here, is the fact that fg of h under the Poisson bracket can be expressed in terms of f of h times g plus f times g of h, as well as the Jacobi identity, which is given by the fact that taking the Poisson bracket of f with the Poisson bracket of g of h and commuting these terms gives 0. So the conclusions that we gave is that we introduced the six-vertex model, the R matrix, and the Hamiltonian flow. And we established similarities using the Poisson bracket for computing action angle variables of the Kamasa-Holm partial differential equation, nonlinear Schrodinger's equation, and the inhomogeneous six-vertex model. And we discussed how to use the Poisson bracket from the action angle variables and other arguments for determining that integrability of the Hamiltonian flow can be deduced and holds for the inhomogeneous six-vertex model. And thanks for listening.